Okay, this week we're starting again with set laws, and hopefully you've had some opportunities to look at the set laws already and become familiar through the mastery exercises and from any of the questions on the Canvas lecture page. But this week what we're going to do is we're going to learn how to do a full proof. So in this example, I say I want you to simplify A or B, or B and C, all negated, as much as possible. So unfortunately, there's no set algorithm to how to do this. So there's not just guaranteed steps that take you from one step to the next. But I'll give you an example of what I did, and I'll give you some heuristics, some strategies to doing these. So if we have A union B, union the negation of B and C, the first thing I usually want to do is I want to get rid of the negations outside of the brackets, get rid of those complements. So I used De Morgan's law in the first step to take that complement and to distribute inside, and then of course I flip the sign from and to or. And what that lets me do is it makes sure that all of the complements are just negating a single thing rather than like a group of things. So at this point, what I see a B, I see another B complement. So B or B complement, that would give us the universe if we got that together, which would be perfect. And I also see that all of our operations are the same. So it's or, union, union, union. That means that I can move the brackets around as much as I want. So my strategy in lines 3 and 4 are to get the brackets together. So instead of A union B brackets, then B complement union C complement in brackets, what I do is I take the leftmost side and I bring it so that way B union B complement union C complement is a unit of 3. Then I take those inside brackets and I move them around B union B complement. Now, what I want to say is you don't have to show this step. Because all the operators are the same, they're all unions, or maybe they're all intersections, we can just move the brackets around as much as we want. I'm just explicitly showing you the laws in each case. Now, in the next step, I finally have B union B complement together. Now, using the complement law, and again, using this sort of picture here, this is B, B complement. If I take the union of these, I'm essentially taking the entire thing in the universe. So I'm simplifying B union B complement into the universe itself. So now instead of B union B complement, I have the universe here. What I'm doing next is I'm using the commutative law to swap the positions of these. Once again, this is an optional step. I just want to showcase how the laws work. But now that I have C complement union the universe, well, I can use what's called the domination law to simplify that down to the universe itself. And as a way of showing this, if I have, imagine this is C complement in the universe, well, I'm taking everything in C complement, so that's there, but I'm also taking everything in the universe, so I'm taking all of this stuff, and that simplifies down just to the entire universe itself. So in line 7, now I have A union the universe, and finally I can use the exact same law again on A union the universe to get down to the universe. And once again, if I were to draw this, there's A, there's the universe. I want everything that's in either A or the universe, so it just gives me the entire thing back. Anyway, what have we really done here? Well, we've shown that instead of having this set, this nasty set, we could instead just write this, and it means exactly the same thing. So, if A is something like the set of dogs, B is something like the set of things that are red, and C is something like the set of things that are happy, instead of saying I want all the things that are dogs are red, or the things that are not red and happy, I could just instead say I want everything in the universe, because it means exactly the same thing, and we've proven that using these laws. We've used equivalencies step by step to show that this giant thing is the same thing as just this small little thing. And when I say big thing and small things, I mean in terms of sets. The universe obviously is much bigger than everything. So here's some strategies for these proofs. Because it does require some creativity, and because of that, you're going to have to practice a bit. So there's a few extra practice questions on the lecture page on Canvas to try after we go through these heuristics, as well as one that we'll do in this lecture video. So the first strategy is to use the complement law as much as possible, as early as possible. So when you see something like f minus g, or you see any of these different symbols, convert that. Convert that into f intersection g complement, because we don't have any rules that deal with the set difference symbol, f minus g. There's no other rules. So translating that into f intersection g complement is good, because now we have an intersection to work with, and we have a complement to work with. If you ever see two double complements, get rid of them. Like, two negatives make a positive. Dealing with double negatives is a lot more work than just dealing with no negatives at all. So if you have something like f intersection g, and you have a double complement there, just get rid of the double complements. Instead, change that to f and g. Well, that sounds inappropriate, sorry, but that's just how we say it. 3. If you have a set and its complement together, then use the complement law to change that to a universe. Or if you have G intersection G complement, change that to the empty set. So getting things like the universe and the empty set is really helpful, because then we can use identity laws and domination laws to simplify other sets. Because when you have a universe and some other set, or an empty set and some other set, one of those is always going to cancel at some point. It's just, is it the universe, is it the empty set, or is it the set itself? And that depends on the operator. So in this example, I have G union G complement inside brackets. So I'm using the complement law to change that to the universe. And then I have the complement of the universe, and it just so happens that the complement of the universe is equal to the empty set. And the same thing, the complement of the empty set is the universe itself. So it's sort of like saying the opposite of everything is nothing, and the opposite of nothing is everything. Okay, so the main thing you're doing first for strategies is use the complement law as much as you can. That's your main priority. Secondary priority are to use the domination laws, the distributive laws, and De Morgan's laws. So the domination law is great. If you have an empty set, you have a union, or if you have an empty set, if you have a universe, you can try to simplify other sets. So here I have P or Q. We can just treat this as one set. I have an intersection, I have the empty set. So I can use the domination law here to just reduce this entire thing to the empty set, because I want all the things in common with P or Q and nothing. Well, nothing is in common with nothing. So we just end up with nothing here. The next big law you should be using when you can is the distributive law. This is when you have alternating unions and intersections. So it's nice to expand them, and it's also nice to simplify them. Because when you expand them, now I have two different sets of intersections I can work with. But this also happens in reverse. So let's say you have something intersection H union something intersection H, and I see a common set here. Because I have a common set, I can reduce them. I can change that. So this one does take a bit of practice. It's a lot of these laws, I can't really guide you through how these work. I showed you the Venn diagrams. That's about the best that someone can actually show you how these things work. A lot of it really is just practice. So the more practice you get with this, the more familiar you become with them. And as always, keep a sheet, keep a reference of all these laws beside you at all times. It helps. The last main priority you should have is De Morgan's laws. So whenever you have anything with a union, or you have anything with an intersection, and you have a complement on the outside, distribute that. Put the complements inside. That way, when you put the complements inside, you can start moving things around when it gets convenient. And you know what to do with complements. So if I have not F or G, another way of saying F union G with the complement around the entire thing, I can distribute the complement inside to get F complement G complement, and then I flip the OR to an AND, or I flip AND to OR. So this is a general priority list. This does not tell you exactly how to solve and how to simplify things, but these are things you should be looking for at every step in this priority. So I'm going to do an example here. If you want to try this, please pause the video and try this yourself first. However, if you're still a little bit confused, you can watch me do it, and you can try some more practice questions on Canvas. It's up to you. So I want to show that A and B and not A and C, or A intersection B intersection the complement of A intersection C, is the same thing as A intersection B minus C. So what I do with all of my proofs is I start by writing out exactly what I've started with. So the leftmost side. And then each step, I give it a number just so I can organize it. And what I'll do every time I use a law, I write the new set and I write what law I used. So the first thing I see here, I see a complement outside of brackets. So my first step is I want to distribute the complement inside the brackets. So I am going to use the Morgan's law to do this. So I will get A intersection B. I'm not touching that part. Intersection. Okay, now I'm distributing the complement. So I'm going to get A complement union C complement. This is the application of the Morgan's law. Okay, what next? Well, I have A intersection B, intersection A complement union C complement. So when I stare at this, there's nothing immediate that comes to mind. But what I do notice is I have an intersection here and I have a union here. So I have alternating signs. And then I have this set on the outside. So I'm thinking now, okay, I can use the distributive law. Now, I picked this example because this is a somewhat complicated use of the distributive law. So what I'm doing is I'm distributing this entire set, A intersection B. I'm going to do this with blue. I'm distributing it to A complement, and I'm distributing it to C complement. So on the left side, I'm going to get A intersection B, intersection A complement, and I'm going to take the union of that with A intersection B, intersection C complement. Okay, so I've used the distributive law here, and it does look a little bit different because instead of just having one set nicely on its own here, like say X, I have a complex set. I have A intersection B. But if we just replace A intersection B here with X here, you'll see it looks exactly like the distributive law. So X intersection A complement union C complement. Well, this is the same thing as distributing X intersection A complement, X intersection C complement, and then taking the union of both of these. It just so happens that this X is the same thing as A intersection B. So it looks complicated, but it's exactly the same application. So please see that again and look at the law sheet if that is a little bit confusing. Okay. On the right side, immediately, I don't see anything nice here. But on the left side, ooh, I see an A, I see an A complement, and I see that all the operators are the same here. So I want to get the A and A complement together. So what I'm going to do now is I'm going to use the commutativity laws, and I'm going to use the associativity laws, and I'm going to get those together. So if I reorganize this, I'm going to get, how should I do this? I'm going to switch B and A around, and I'm going to move the brackets around A intersection A complement. Then on the right side, I'm just going to keep everything the same for now. I'll deal with that stuff later. Okay, this is beautiful because now I have A intersection A complement, and I can use the complement law. So A intersection A complement, what's in common between those two? The answer is absolutely nothing. So this will reduce to the empty set. So now I have B intersection the empty set, union everything from before. So A intersection B, intersection C complement. Now I have B intersection empty set. So what's the shared elements between these two? Well, the answer is nothing. It's the empty set. So this is the domination law of the empty set. So on the left side, we get the empty set. And now I take the union with A intersection B, intersection C complement. Okay. At this step, 7, I have the empty set union something else. So this is a case of the identity law. The identity law says if I have the null set, the empty set, union anything else, I get that anything else back. Because I'm taking elements in both the empty set and A intersection B intersection C complement. So I'm just left with everything in A intersection B. Should use orange to be consistent here. A intersection B, intersection C complement. Okay. Now, we shouldn't forget our final goal here. The final goal is to get A intersection B minus C. So I can do some reverse engineering here. I see B minus C, right? Well, the complement law says this is the same thing as B intersection C complement. So I want to try to get these together. So what I'm going to do is I'm going to use, in this case, now let's go back to green on 8. I'm going to use the associativity law to move the brackets on B and C complement together. So I'm going to get A and B and C complement. And now I don't quite have enough room here. So what I'm going to do is I'm going to get rid of this first line here, and I'm going to move everything else up. Okay, so what I'm going to do in step 9 now is I'm going to use the complement law on B intersection C complement to change that to the set difference sign. So now I get A intersection B minus C. And at this point, I have now completed my proof because I've gotten to what I want to get to. So using these 8 steps or so, the first step was an assumption. I have shown that A and B and not A and C is the same thing as A and B minus C. So this is a complicated proof. It's more complicated than the ones that you'll see on any assignment or any test, really. I show you a really complicated one, so that way, if you can master this one, then you should be able to do the other ones on your own. But that's it as far as the next part of set laws. Again, the key here is practice. If you ever get stuck during these, feel free to ask some questions and ask for advice, and I'll try to point out what to do next. But as always, if you have any questions, discussion board, email, I'll answer you when I can.